So I will be presenting my PhD work, which is single chip dynamic nuclear polarization microsystems. So here is the outline of my talk. First, I would like to make an introduction and explain you our motivation on realizing such systems. Then I would like to give you some example microsystems that we realized on 3 subsections, which are 10 gigahertz DMP microsystem, 200 gigahertz DMP microsystems. And finally, I would like to show you some preliminary research on low power oscillators for cryogenic dynamic nuclear polarization microsystems. So I'm sure you already know that nuclear magnetic resonance has a wide range of applications, from medical imaging to structural information of chemical compounds. It is also used in non-destructive testing of biological samples, as you can see here, which was measured with a single chip NMR microsystem. So you might ask, why single chip is good for doing magnetic resonance? So first of all, what we know is that for the optimum signal-to-noise ratio, it's best to optimize the sample size to the coil size. So if we think of a sample size that is much smaller than the detection coil, you can imagine that the spins inside these samples induce only some signal around this region, and the rest of the coil just generates noise because of its resistance. So the best way to optimize the SNR is to match the sample size to the coil size. Then we take this matched sample and coil inside this very big magnet with actually not such a big homogeneous magnetic field region. And if for very small samples, a nanoliter and subnanoliter region, actually this size corresponds to something like around 100 micrometer. So this 100 micrometer coil, with a sample of, let's say we put something like a polymer that has some protons, would generate a signal around some picovolts to up to a nanovolt. Then we need to do some electrical connections to the outside of the magnet if we place the first amplification stage outside of the magnet. And what is important here is that when we do these long connections, it's very important to do the power matching of the coil to the input stage of the amplifier, not to lose the signal. So this brings up some design limitations of already to the amplifier and the coil. What happens also on these very long cables is that the signal could be reduced, noise could be introduced, and there could be also some background signal on the signal level. So that's why if we place this first amplification stage into next to the coil, for example, like we did in single chip magnetic resonance systems, we can place actually the amplifier in very small micrometer distances compared to the meters of cables that we can use in conventional systems. There are other possible advantages of also the single chip approach. One could be noted as wired and wireless approach inside living cavities because of its very small size. Here I choose an example from Jonas Handwerker, and in this example they realized a CMOS needle in a CMOS chip, an NMR needle, where they placed inside a mouse brain. And this is a wired example actually. And this coil size actually is again on some hundreds of micrometers range. Another possible method that we can extend using the single chip approach is the parallel spectroscopy. So because of very large scale integration possible with the transistor technology, what we can do is to integrate several coils with several receiver and even excitation systems, such that we can, as given in this example by Jan Sanders, that there is a possibility to integrate single chip arrays of NMR receivers, that is possible to detect 8 different samples at the same time. Another example by Hakoli is that there is this chip NMR biosensor. In this case, it's a microfluidic chip in combination with a PCB, but is again possible to do parallel spectroscopy. Another possibility of single chip approach is that the transistor technology is adapted for low temperature experiments. So if we are interested in low temperature magnetic resonance experiments, the transistor technology is already better at low temperatures. So here I picked an LNA example that shows that the noise figure is reduced by the reduction of the temperature, and also the gain of the amplifier is increased. This is just the natural possibility that is available with the transistor technology. Another possible approach that we can explore is low-cost microwave sources for dynamic nuclear polarization applications, which is actually the co-integration of the microwave source together with the NMR circuitry. So if we go back to this slide where we can do lots of things with nuclear magnetic resonance, is actually there is just one major disadvantage of this approach, is its sensitivity. So this brings us to the dynamic nuclear polarization. So if we look at spin polarization at 7 Tesla at 300 Kelvin, you see that for protons, only 25 parts per million of these proton spins are polarized. And at the same condition, if you look, for electrons, it's 1.6%. So if we find a method to increase the proton polarization up to electron spin polarization, we can have 660 times more polarization. So what does this mean? This is actually already very well-known technique again. And if you look in the electron spin S coupled with a nuclear spin I in this below schematic, what happens is that at room temperature, because of the thermal equilibrium, nuclear polarization without ESR excitation is similar to this drawing. So there's a very little polarization difference between upstate and downstate. This means the NMR signal without ESR excitation will be like in the red curve, which is a small signal. And if we take microwaves and start exciting this coupled system, nuclear polarization with ESR excitation could be increased much more. So we have a big polarization difference between the states. This gives an NMR signal with ESR excitation, which is much more, as you can see in this graph. So we need microwave sources to be able to do this. And here is the state of the art of microwave sources. So before mid-90s, the DNP experiments were actually limited to low fields and low frequencies, low microwave frequencies. And by the introduction of gyrotron, first experiment at 5 Tesla was made possible. And today, even DNP experiments up to 20 Tesla are possible. But gyrotrons are very high cost and high maintenance systems. So researchers started to adapt different kind of technologies to realize microwave sources. One of them is to utilization of diode sources with the amplifier and doubler chains together with waveguides. And another one is the arbitrary waveform generator combination that was actually presented very recently, published very recently. And this is to do frequency swept dynamic nuclear polarization experiments. However, it is stated that still the diode sources compared to gyrotron sources are not more efficient in terms of microwave power per cost. So we can still say the gyrotrons are the mainstream devices for used for microwave sources using these experiments. So here is our motivation. What we would like to do, this is the general gyrotron system where you can see on the right there is an NMR magnet, and on the left there is a gyrotron, and in between we have a microwave waveguide to carry the microwaves to the sample region effectively. And what we propose is here is to introduce single chip DNP microsystems 4 nanoliter and subnanoliter samples to place in the NMR magnet and perform DNP experiments without external microwave sources such as gyrotrons. Here's our measurement setup that I would like to show you such that you can imagine better how we do maybe our experiments. This is the magnet, and this is what we call probe. It's basically a metallic rod with cables. And at the end of this probe, we have 2 SMA connectors with 12 twisted pair cables connected to this black DC connector. And we connect at this end a printed circuit board, which carries actually the single chip DNP microsystems. So to realize these single chip DNP microsystems, we need to do co-integration of electron spin resonance and nuclear magnetic resonance detector on a single chip. For this, we investigated integrated circuit technologies to understand which one is suitable to use. So these are the main 3 that we investigated. The first one is the complementary metal oxide semiconductor, which is the so-called CMOS. It is the most widely used technology. So because of that, it is low cost, it has moderate power, and has a very high level of integration. So you can have very good interconnections between different kind of levels in the circuitry. And if you look in silicon germanium technology, we see that it is much easier to reach higher frequencies with this technology because of its cutoff frequency of the available transistors in the technology. It provides moderate to high power, microwave powers, and it has also high integration level. And there's also SIGA by CMOS options where you can have also the CMOS available in the silicon germanium technology. And finally, we investigated high electron mobility transistor technology, especially indium gallium arsenide technology. This technology is also suitable for high frequency applications. It is also optimum for low power consumption operations. However, it has low integration level, which means it doesn't have as many as interconnection metal layers at the same quality compared to CMOS and silicon germanium technology. So with the CMOS technology, we realized the 10 gigahertz DNP microsystem. With silicon germanium, we realized the 200 gigahertz DNP microsystems. And finally, with the high electron mobility transistor technology, we investigated low power oscillators for cryogenic DNP microsystems. So here I would like to present our first prototype, which is a 10 gigahertz DNP microsystem. Here you can see the chip photo, and here a close-up of the microcoils where we place a sample and where the main part of the experiment is actually happening. You can see there is this 2-turn coil, which is the ESR microcoil that is connected to ESR electronics. And at the inside of it, you have this many-turn NMR microcoil, which is actually a 10-turn microcoil. And the NMR microcoil is connected to the NMR circuitry. So the DNP microsystem consists of 2 main circuitry. The first one is the ESR circuit that you see on the right. And the second one is the NMR circuit that you see on the left. So the ESR circuit is a 10.7 gigahertz oscillator. What it does is that we send some DC power, let's say 1.8 volt to this oscillator, and it starts oscillating and is generating 10.7 gigahertz microwave excitation in this 2-turn ESR microcoil. Then we go to the NMR microcoil, which is connected to the NMR circuitry. NMR circuitry is a broadband transceiver. So it has a transmitter and receiver components, as you can see here. So when we do the experiment, first we send the the excitation signal through the transmit channel, and we stop excitation, And we start acquiring the induced NMR signal by switching on the receive channel, which consists of LNA, down conversion mixer, and further amplification. So we did some microwave magnetic field characterizations. On top, you see 3 figures, which shows the COMSOL simulation results. So first, we do some circuit simulation to estimate how much current that runs in the coil. Then we place this current in the COMSOL simulation to plot how much microwave magnetic field is generated by this coil, by this current on this coil and in the effective sample region where we place our liquid samples that I will show later. And as a second approach, we did some experimental, some measurements, and we placed a BDPA at the center of these 2 concentric coils, and we did EPR-ESR experiment at several biasing conditions, and we measured how much is the broadening of this ESR signal, and from that we extracted the microwave magnetic field, which is B1E here. And at the maximum bias condition, we reached to experimental microwave magnetic field of 70 microtesla at the center of the concentric coils. So to test how this system works, we did some Oberhauser DNP experiment. So our sample is Tempol water solution. We took the sample and placed inside this 200 micrometer capillary. And we placed the capillary, as you can see, like this, on top of the coil, such that the capillary surface touches the chip surface. And first, we do a continuous wave electron spin resonance experiment by sweeping the magnetic field, and we get the ESR curve. Then we go one of the peaks of this ESR signal and stop the magnetic field, the B0 at that magnetic field. And we start doing an NMR experiment. And as a result, we get this blue curve, which is the DNP NMR curve that is actually measured in 8 minutes. Then we turn off the ESR excitation. This means we close the source that gives the DC voltage to the oscillator. So the oscillator is off. And in this case, we repeat the NMR experiment again. And you can see this red one, which is multiplied by 5. And this is extracted of around 14 hours. And we can see that the enhancement is, as a result of this curve, the enhancement is minus 42. We did some study of the concentration and the degassing, and with a 10 millimolar degassed sample at the maximum micromagnetic field applied by the oscillator, we reach an enhancement of minus 50 Oberhauser with this microsystem. We also did some solid effect experiment by cutting some BDPA doped SEBS polymers. As you can see in this picture, we place it again on top of the chip with contact. It can stand on its own. It doesn't need any glue because it's sort of a sticky material. Then again, we did continuous wave ESR experiment, as you can see here. And we did a solid effect experiment, again on the right and left side of this ESR curve. You can see here a swept experiment. Each point in this graph is actually a peak point of an NMR measurement. And we can see that when we are on one of the solid effect conditions, we can reach almost an enhancement of 20 at room temperature with this system. For further investigation, we also did some ESR measurement at cryogenic temperatures, which shows that it's possible to do to work with this system at 180 Kelvin, also below down to 15 Kelvin. So these measurements are done BDPA doped polystyrene samples. And these are actually indicating that the possibility of doing a low temperature DNP experiment also with this system. Well, very happy with this result. We decided to increase the operating frequency such that we can reach the gyrotron magnetic fields, actually. So we decided to realize 200 gigahertz DMP microsystem. Here is the, again, chip photo and the schematic of the circuitry. You can see again at the right bottom figure here, concentric coil, which are ESR and NMR microcoils. This time you see ESR microcoil is in the middle of the NMR microcoil, and it's actually much smaller. This the main reason of this is because at 200 gigahertz, the self-resonance of inductors are getting closer and closer to this frequency. So to oscillate at 200 gigahertz, we need to make the coils much smaller compared to 10 gigahertz. So that's why we made this ESR microcoil of around 50 micrometer diameter. And around that, we made NMR microcoil of 21 turn, 3 turn at each layer with 7 turn at each layer of 3 metal layers. So again, these ESR and NMR microcoils are connected to 2 main circuit blocks, which are ESR and NMR microsystems. So ESR circuit this time, you can see on the right, is an 200 gigahertz voltage controlled oscillator. This means we have a V-tune voltage, as you can see on the right, which it is used to tune the frequency of the oscillator, such that we don't have to do field swept experiment, but we can also do frequency swept experiment. And this is also another implementation in the circuit, is to do amplitude detection. So what you can see here is that we model the ESR microcoil here at the center. And at the middle of this ESR microcoil, we take a cable out, so a connection out. And with one connection, we go to the biasing current, such that we bias current through this node. And in the second, through an inductor, we go to the VESR node, which is the output of the this ESR circuitry. What happens is that when we do an ESR experiment, it's actually what happens in an oscillator is that both the frequency of the oscillator is changing and the amplitude of the oscillation is changing due to the ESR event. So to detect using an oscillator, we can either do a frequency detection or an amplitude detection. And in the 10 gigahertz system, we were taking directly the output of the oscillator and we were doing frequency detection. And in this case, at 200 gigahertz, so since it's very hard to take 200 gigahertz signal out of the chip, we do amplitude detection on chip, such that we just take a DC cable out, and the ESR amplitude is decoded at this node because of the differential structure of this oscillator. So it has the frequency tunability, and it generates of around 10 Gauss V1 at the center of this ESR microcoil. Then around we have NMR microcoil, which is connected to the NMR circuitry. This time NMR circuit is not a transceiver, is just a receiver. So the NMR excitation is down outside. So what we do, we connect the NMR microcoil to LNA mixer, down conversion mixer, and further amplification. So another thing that we implemented in this design, a secondary design, let's say, is the DNP array microsystem. So in this case, what we do is actually we take 4 ESR oscillators and couple them with capacitors at the output, as you can see here. This makes sure that these oscillators are locked and working at the same frequency and exciting a larger sample area, because as I mentioned that what we can do is around 50 micrometer ESR microcoils, and when we couple 4 of them together, the sample volume is increased up to a factor of 8 actually. But of course, there is a cost, which is the power consumption of this chip is much higher, because there are now 4 oscillators that consumes 4 times more compared to the previous previous DMP microsystem. So here I would like to show you our measurement setup. We have again on the left our printed circuit board, where we placed the single chip DMP microsystem on top of it. And you can see here a close-up of this microsystem with bonding wires to do some electrical connections to this chip. And you can see NMR excitation, as I mentioned before, is done outside. So we do it on PCB, and this excitation coil is also visible here. Here we have again a close-up of these two concentric coils, where we placed a small sample on top of these two coils. Here, what I would like to show you is the instrument, the outer instrument that we used for ESR excitation and detection, are just a DC source that biases the DC of this oscillator. And to do continuous wave experiments, we do modulation. And for that, we use lock-in amplifier, and we do magnetic field modulation here. Then we take VESR, and this actually, the ESR signal further amplified on the chip to increase the amplitude of the ESR on the chip, it's on the PCB, so printed circuit board. You can see that there is this black component here, which is a low frequency amplifier that further amplifies the ESR signal. Then we just go to a DC cable and go out, because those two AC coaxial connectors, SMA connectors, are occupied for NMR excitation and LO signals, actually. So ESR connections are completely DC. Here I would like to show you how we can do frequency tuning of this oscillator by just a DC voltage bias. Here this DC voltage is represented with VT, and because it's a tuning voltage. And so you can see at room temperature for the single system, at 300 Kelvin, we have around 3 gigahertz of tuning. And for the array system is actually because of the parasitics that is unavoidable when we do this such close design, the frequency tuning is reduced to 1 gigahertz. There is also additional tuning available by the DC biasing of the oscillator. So here I would like to show you the DNP experiment results that we get with the 200 gigahertz DNP microsystem. You can, so here is the chip photo of the computed system. As I mentioned before, we placed a BDPA doped polystyrene sample on top of the ESR microcoil, where the 200 gigahertz excitations are most efficient. And you can see that we did experiment at 15 Kelvin and 100 Kelvin. And at 100 Kelvin, we reach enhancement of around 10. And at 15 Kelvin, enhancement increases up to 50. And how we do this experiment is by just changing the tuning voltage. What happens here is that we set the tuning voltage to a value. This corresponds to an ESR oscillator excitation, let's say 201.5 gigahertz. And at that ESR excitation, we perform an NMR experiment and report the maximum amplitude that we can get from that NMR signal. And with this, we change the V-tune voltage, and correspondingly, we change the oscillator excitation. And when we reach the solid effect condition here, at let's say 201.6 gigahertz almost, we have 50 times more NMR signal compared to when this ESR signal was not at the right point. Accordingly, we also tested the DNP array microsystem, which works at the central frequency of 190 gigahertz, is again because of the parasitics that reduces the oscillation frequency. And in this case, we did experiments from 300 Kelvin down to 200 Kelvin. And at 300 Kelvin, we measured BDPA-doped SEBS samples we selected this sample because it's more flexible and is actually has narrower line width, so it would be easier to see the signal in the spectrum. And you can see that at graph B and C, we have different volumes of this sample and different experimental conditions that shows both solid effect condition and some Overhauser, some enhancement at the Overhauser condition. And the reason that the B actually looks larger is because of the repetition time becoming much smaller, is what we think actually most probably because of this repetition time, because the solid effect needs more time to recover compared to Overhauser effect. And at 200 Kelvin, actually, we again used BDPA-doped polystyrene sample, and we did again an experiment by sweeping the tuning voltage. And you see when we reach the right condition of solid effect, the signal is enhanced almost 20 times. So if I do a summary of 200 GHz DMP microsystems, so this system works around 7 Tesla. With single oscillator microsystem, we have enhancement of around 10 at 100 Kelvin and 50 at 15 Kelvin. And with the array microsystem, enhancement reaches 20 at 200 Kelvin. So if we look at enhancement reported in the literature for BDPA-PS, at a bit higher magnetic field, a similar enhancement is reported at of 12 is reported at 100 Kelvin. So a bit of lower magnetic field at room temperature, actually an enhancement of 10 reported. And with a highly deuterated polystyrene, BDPA-doped polystyrene sample is actually at higher magnetic field and similar temperatures, 8 to 15 enhancements have been reported. So if we look at the system, so NMR only spin sensitivity of the NMR receiver is around 310 to the 13 spins over square root of hertz. And in the DMP condition, this spin sensitivity is improved by the factor of the DMP enhancement. So we did some microwave magnetic field characterization experiment also with this system. So at 200 gigahertz, the simulations are actually taking much longer time, and they are not as definitive as the ones that you can do at 10 gigahertz. So we did some experiments again with BDPA, but very small BDPAs on top of the chip that indicates a micromagnetic field of around 10 Gauss. And the simulations that we did with the circuit simulator was indicating something around 6 Gauss. So if we look at the micromagnetic fields reported in the literature, it varies between 0.5 to 15 Gauss. But in these publications, it's actually stated that the micromagnetic field of 15 Gauss might not be so necessary because the maximum enhancement is not reached at 15 Gauss. So additional possibility of with this system is the easy frequency tuning up to 8 gigahertz, because we have 3 gigahertz available with the tuning voltage, and with the other biasing voltages, we can tune plus 5 gigahertz more. So this is all from the 200 gigahertz DMP microsystem. And with all these results, we actually also did some low power oscillator studies using hemp technology for cryogenic operation. So for this, we actually first investigated the hemp technology. So you see the picture of the transistor. We place this transistor in, again, the magnet and at low temperature condition. And we characterized it with a semiconductor parameter analyzer. So we did some characterization measurement, actually with the first DC characterization measurement. What we can say, the current gain is doubling by the reduction of the operating temperature from 300 Kelvin down to 1.4 Kelvin. So we did further characterizations to understand what is the mobility. and we extracted the mobility to be also doubled from 300 Kelvin to 1.4 Kelvin. So the mobility is also increasing with the reduction of the temperature. So we realized two systems with the HAMT transistors, which are 11 GHz oscillators and 35 GHz oscillator. And in these two oscillator, the power consumptions, the DC power consumptions of these oscillators are actually 90 microwatt at 300 Kelvin. So at the time, when we checked the literature, this was the lowest power consumption microwave oscillator reported at the literature. And when we reduce the temperature to 1.4 Kelvin, 35 GHz oscillator consumes only 15 microwatt, while 11 GHz oscillator consumes 4 microwatt. So why this reduction of power is important is that because there are two factors. The first one is the cooling power available in the magnet. So if the chip consumes a lot of power, the magnet might not be able to, the sample region might not be able to cool. Another thing is that by the chip, there would be local warming of the sample that we probably won't be able to detect with a bit further away temperature samples sensors. So we also did some electron spin resonance experiment, especially with this, what I did is with the 35 GHz oscillator. With the 11 GHz oscillator, it was a collaboration work with another previous PhD student in our group. So we tested this oscillator for ESR down to 10 Kelvin, and we reach spin sensitivities down to 10 to the 7 spins over square root of hertz. So as a conclusion, here are the main things that I did during my PhD, which are the single chip DNP microsystems. So with the CMOS, we realized this 10 GHz DNP microsystem, and you can see that it was working at 0.37 Tesla. We tested it 300 Kelvin with ESR, NMR, and DNP experiment, and down to 15 Kelvin, we performed some ESR experiments. This chip was consuming between 130 to 260 milliwatt DC power. And the microwave magnetic field generated locally at the center of these two concentric coils was varying between 10 to 70 microtesla. Then we realized a 200 GHz DNP microsystem with the silicon germanium technology. This chip was operating at 7 Tesla, and it was tested from 300 Kelvin down to 15 Kelvin. And the total power consumption of this chip was varying between 35 milliwatt to 65 milliwatt, depending on the biasing condition of the ESR oscillator. And the microwave magnetic field generated by this chip was around 1000 microtesla at the center of these concentric coils. So finally, with the high electron mobility transistor technology, we realized an ESR detector that was working at 1.4 Tesla, and we were able to test this from 300 Kelvin down to 1.4 Kelvin. And the power consumption of this oscillator was varying between 90 to 15 microwatt, which is much, much smaller compared to the other systems. So this was actually designed as an ESR detector. So also the microwave magnetic field was minimized to 1 microtesla, not to saturate the ESR samples in continuous wave experiments. But also at such low temperatures, maybe below 1.4 Kelvin, also the required microwave magnetic field is probably much lower for the DNP experiments. So if we look at the outlook of this work, one very important thing that we can do is to increase the array number. So we can have larger arrays to increase the volume, such that we can work with much larger samples. And we can also have arrays to have separate systems to do parallel spectroscopy. So not only the arrays of the ESR oscillators, but the arrays of DNP microsystems, such that we have separate oscillators for excitation and separate NMR circuitry to do parallel DNP experiments. Another thing that we can do is to lower power consumption to generate similar microwave power with the oscillator, and this lower power consumption also for 200 gigahertz system, such that we can cool even more. So with the 200 gigahertz system, we have already observed that we can cool down to 10 Kelvin with the cooling power available in our magnet. And if we were able to reduce the power consumption, we could also go even lower power temperatures to do the NP experiment. Another thing that we can do is to increase the frequency such that we work at higher magnetic fields. This is also possible with the transistor technology, because even oscillators up to 570 gigahertz or even 700 gigahertz are possible with the integrated circuit technology. So here is the first original 140 gigahertz gyrotron oscillator used for DNP experiments. And today it's a very well established and most widely used system around the world. And we believe that for nanoliter and subnanoliter samples, single chip DNP microsystem might be the future. So I would like to thank you very much for listening, and I would like to thank Swiss National Science Foundation for funding all this my PhD work, and of course my supervisor Giovanni Boero, who helped me in every step of this work. We work together with Reza, Alessandro, Marco, Gabriele, and Roberto in all this work, and I would like to thank also them. Thank you for listening. And please let me know if you have questions. Yes.
Thank you very much, Nergiz.
Thank you.
So we can start with the first question from Quentin. So on your 200 gigahertz system, what is the time response of the ESR excitation frequency to the bias voltage? Could you use it to generate frequency swept pulses, chirp or burst?
So it's actually, we didn't characterize this, but we believe it's very quick. So as soon as we set the DC bias voltage, it should very quickly change the operating frequency. So we were actually thinking of using some frequency swept experiment that we didn't realize yet. So we believe it should be possible, but we didn't do this experiment yet.
I had one question. Like, is it because on the center of the ESR and NMR point, is there something, or on the 10 gigahertz microchip, or can you like drill a hole and insert a tube around in your circuitry? You know what I mean?
Yes, I understand. So here, actually, you can do it, yes. And you see there is this opening at the center of the NMR microcoil, and there is nothing here. It's just substrate. So we can drill a hole all through this chip.
And what is the, the diameter is less than 200 micrometers. Yeah,
so it's like 100 micrometer, the inner diameter. So it's possible to do it larger for those sorts of application, of course.
Okay. Thank you. We have a question from Nesrin. So Nesrin says it was a very nice talk. And so how does the background noise in DNP microsystem differ from original systems like gyrotron?
Okay, background noise, what do you mean by the background noise? So I'm not sure.
So I wait for Nesrin to add.
If possible, can you explain me what is the background noise? Or so one thing that we have with this microsystem is actually the background signal. So when we do the measurement of the small samples, there is some leaked signal because this printed circuit board has a lot of protons, and when we excite, actually lots of protons around this excitation coil are excited, and some background signal is also coupled through this. So we need to do background cancellation with this system. But if we just change the material of this printed circuit board to, for example, Teflon, we actually recently did this, and we were planning to repeat the measurements. And in the Teflon, there is almost no proton in the printed circuit board, so this would reduce the background signal dramatically.
Yeah, it was actually this from the board, the question. So, okay.
Yes, I hope that I am.
We have a question from Felix. Regarding the tuning range of the ESR, that is around some percent. What is the main limitation to make the range more broadband?
So actually integrated, there are in the literature integrated oscillators which has a much wider tuning range. So it is possible by more circuit design optimization to increase the tuning range. So this is just, let's say, for tuning voltage, we have only 3 gigahertz, but there are other oscillators that is able to tune up to 20, 40 gigahertz on top of 200 gigahertz. So this is definitely possible by changing the design such that you make more dependence on these two varactors, because these two varactors, when we apply the tuning voltage here, they change the capacitance. And if this capacitance is more dominant compared to the parasitics around this layout and circuitry, that would be more dominant, determining the operating frequency, and you would be able to increase the tuning range. So this actually, we didn't have time when we were doing the design to optimize this. So we didn't need also much larger range. So we decided, okay, let's do this, but it's possible to do.
We have another question from Walt. What hardware is required for cooling the sample coil combination, and what isolation is needed?
So we are just using these cryogenic magnets to cool the magnet. Here, maybe I show. So this is a closed loop system, and with the helium pumps, it is cooling down the sample region. And what we do, there is this sample region and the magnet is actually isolated. So with this yellow cable, if you can see, we introduce more helium to cool down. So we don't do any isolation between the sample and the chip and the environment gas around, helium gas around. I'm not sure if this answers the
Yeah, it's actually question. All of the probe is immersed in a helium bath.
Yes, so you can, this actually is okay. You can just dip the chip printed circuit board all together inside also a helium bath. So there's no isolation needed.
And Walt adds to the question, how do you regulate the temperature this way?
So we have a temperature sensor on top of the coil here. Do you see my cursor?
Yes.
Okay, so here we have a temperature sensor and a resistor to adjust the temperature. So we just use the software. It is given by the cryogenic, and we set the temperature, and it regulates by measuring the temperature and using this resistor, and by with the flow of the helium gas around, it regulates the temperature.
Okay. So it regulates then the pumping pressure or
With the helium flow, yes. There
yeah,
is a
yeah.
constant helium flow with the pump that pumps the helium, and this regulates the temperature.
Yes. Quentin is adding another question. On your 200 gigahertz, the ESR coil is much smaller than the NMR coil, and your
Yes.
sample seems bigger than the ESR coil. Does it mean that you detect the NMR signal from a larger volume than what you can excite with the ESR coil? In this case, don't you underestimate the DNP enhancement?
Yes, very well explanation. So this is completely true. When we place a larger sample, as you mentioned, what happens is that we measure NMR signal also from the region that isn't excited. So the DNP enhancement is an underestimation. So we need to also do more studies to optimize the sample size, place only on top of the ESR microcoil, such that we are sure that all the NMR signal comes from the excited region, and we can estimate better the DNP enhancement. Thank you.
We have a question from Aziz. Do you have control on the microwave phase?
Do you have control of the microwave?
Phase.
Phase. No, so this is a free running oscillator. Maybe how do I show it? Okay. In both cases, actually, it's a free running oscillator. So we turn on, we apply some DC voltages, turn on the oscillator, and it just oscillates. So we don't control the phase. We can adjust the frequency.
I have another question. So with this design, what is next? Do you want to try to test it with MIS in solid state?
So we have more ideas experimentally. One was already mentioned, the frequency swept idea. The second is to removal of the background by a new piece printed circuit board, and also to like frequency sweeping and maybe abrupt frequency changes, like some sort of pulsing of the frequency. What else we can do? We have actually another system that we designed for DNP that at a bit actually lower field, and with the we aim higher enhancement and study of liquid samples that would go for more benchtop systems. What can be done is to increase this array to many more arrays to increase the sample volume, such that we have larger sample volume to interrogate. And another is to do, let's say, the multiplication of this circuitry on the same chip, such that we have a really parallel spectroscopy. That would be very interesting.
Yes.
Studying of different samples at the same time.
And what is the line width at full maximum in the liquid state of your sample? The NMR signal.
So we didn't measure the liquid samples. We did this high frequency system. With the 10 gigahertz, we did measure the liquid samples.
Yes.
So in this case, maybe I can show you when it wasn't enhanced. So the spin sensitivity of this detector is also around 10 to the 13 spins over square of hertz, but at 300 megahertz. So we would scale it to 16 megahertz. We need to scale it to 16 megahertz to calculate what is the effective spin sensitivity without DNP enhancement.
Yeah. We have another question from Aziz for the future of this microchip. He was thinking, how about integrating microfluidics with this setup?
Yes, that would be actually very interesting, such that we have two systems on top of each other. Actually, maybe I can go back. So in this biological sample study, in our group, a previous PhD student was using this single chip NMR system, and they were producing a microfluidic chip that goes on top of this NMR chip, such that they would trap this RC ovum, as you can see here, to do biological sample studies. So it is also very interesting to combine with the DMP microsystems to realize a microfluidic chip, such that again we study biological samples.